All right. So, in the last class we started discussion on weak turbulence, and I kind of took a toy problem where the fluctuations were moving with a certain speed. In fact, so some of weak turbulence involves um, a linear term which corresponds to Hamiltonian H naught of quantum mechanics. So, the linear term must be much stronger compared to fluctuations. Okay. So, the waves, linear term is driving the wave, but because of nonlinear term which is weak, these waves will get modulated. Okay. They will generate more waves, but the effects are small. So, we showed that the spectrum for wave turbulence with constant u naught is -3/2, okay, under some limit, but there is another theory which is k per -2. So, I showed it in the last class. So, I am going to do some more examples, okay. And so, we will not want to discuss the physics of these examples which are quite complicated, but we are just going to treat it as a mathematical problem, okay. Um, so, I am not expecting you to become an expert of rotating turbulence or even get a full gist of it, but I will show you how to derive the spectrum for rotating turbulence using weak turbulence theory. So, first thing is, what is rotating turbulence? We have a fluid, you can think of a fluid in a container which is like 3D box, which is rotating very fast along z direction. Okay. So, the omega is very fast. So, there will be Coriolis force. It turns out the centrifugal force can be absorbed in pressure. So, we have Coriolis force and there is equation, in fact Navier-Stokes equation, and we can write down the equation of course, but the turbulence is highly anisotropic. It tends to be two dimensional like earth, so because of rotation we are having a two dimensional. So, fluctuation parallel to the rotation is suppressed and there is a fluctuation perpendicular to the rotation, and so we have okay. So, now I am not going to tell you what this u plus and u minus are, these are called helical modes, okay. They satisfy without nonlinear term this simple relation. So, two waves, one plus wave which is I omega and minus wave which is minus I omega. So, they are linear waves, right, and they have the speeds not speed actually. In fact, you can look at here k. So, by the way, the omega is the rotation. In fact, I should really use capital omega. So, let us use capital omega. So, this is a rotation frequency, that omega, okay. So, we can write down. So, I will not want to derive it, actually in fact is small omega only. So, this is the frequency. So, this was small omega which is the frequency which is connected with capital omega is 2 omega cos zeta. What is zeta? So, this is z axis and a wave number k, okay, this vector. So, this angle is zeta. So, omega is not linear in k. So, this is not a wave, I mean this is not like a non-dispersal waves, this is dispersive waves, no, omega is not linear in k. So, it is not like normal waves where omega is proportional to k. So, this is property of this system. So, omega is proportional to 2 omega and there is k dependence which comes by zeta, right. So, cos zeta will be k parallel. So, parallel along z direction, k parallel by k, right. So, this is my omega. Now, I play the same trick. So, I need to write down this energy transfer, right. We need to write down the flux formula. So, some of you were absent in the last class. So, we need to write down how much energy is going across scales, okay. So, I did in the class this energy transfer from P to K, right. This is a Q is a mediator and this is pretty complex formula which involves is a for a given triad. So, this is a triad K K prime P Q. So, we had seen this before and they are angles. So, in front of K is alpha, in front of P is beta, in front of Q is gamma. So, these are formula, okay, it has been derived before. You can look at my book where I have all these derivations. So, this is the formula which is connecting this interacting modes. What is SP and SK? They take value plus or minus 1. So, these are helical modes. So, plus helical plus mode is circularly polarized clockwise and minus will be anti-clockwise. So, these are circularly polarized waves, in fact they are helical modes. So, we have these nonlinear interactions here. Okay. So, this we have studied in well briefly in our course. So, this is nonlinear interaction and that leads to energy transfers across scales. So, I can compute the flux and the flux formula is given this energy transfer, I just integrate. So, flux is energy coming out of a sphere of radius k. Okay. So, this is given by that. Okay. Now, I will not, I discussed this slightly in the last class, but this is that energy formula. So, I integrate. So, giver is inside the sphere and receiver is outside the sphere. K prime is the receiver. So, this is a k or k prime, k and k prime are same. Well, k prime equal to minus k. Okay. So, now since I said this is 2 dimensional, quasi 2D. So, flow tends to become quasi 2 dimensional. So, I am going to divide this integral dk, which is 3 dimensional integral, into k perp and k parallel. So, this is dx, dkx, dky, dkz, which is kx, ky are here and k parallel, which is kz is that. Similarly, you do it for dp, this one. Okay. Now, so there is one more term which I missed. So, there is a delta function, delta omega minus omega k minus omega p minus omega q. Okay. So, this I derived in the last class. So, this is a coming from the time dependence part. Okay. So, this is this part. Now, I am going to just count the dimension. This integral is reasonably hard to do, but we will just count the dimensions. So, let us see. So, this omega, okay, there is a so basically we get a delta function because of the time dependence part and that delta function basically has dimension of frequency and frequency is coming from here 2 omega which is here and k parallel by k perp. The frequency comes below and if you remember for hydrodynamic turbulence the frequency was 1 over nu k squared comes below, no, in the denominator. So, same thing here, but here I do not have viscosity. In fact, I have this frequency e to I omega t and that frequency is coming here. Now, k parallel will cancel with this k parallel. Well, you will get a log stuff, but that is non dimensional, that basically dimensionally it cancels. So, how many, what is the dimension I am going to get? I get here k squared, okay. So, and it is a, so this k parallel will cancel and there is a k squared here, there is a k squared and it is a 2D. So, this k squared will be k perp squared and I get from here k perp and k perp. Okay. So, there is a k parallel is cancelling here and I get k perp squared and I get here k perp squared and dp perp will also give k perp square and p parallel is this k parallel and this k going up. So, case 7, this something is odd. So, this k parallel is here, okay, and I am over counting this k perp. So, this energy, so what we got, what we get here is this Ck, which is modal energy, right. So, if you look at the derivation, I did that one, C, we will get 2 of the correlation functions Cp, Ck, Cp. Now, I need to convert that to 1D spectrum. So, I convert this to 1D spectrum which is going to be Ek, for 2D is going to be k perp, right, 2D will k perp and this is going to be Ep divided by K perp. So, these 2 K perp will cancel with these 2 K perp, okay. And this is anisotropic. So, I am going to write as K perp K parallel, and this is P perp P parallel, okay. So, now we get basically, so this K is a quasi 2D. So, K is essentially K perp, no. So, I can replace these by K perp. So, I get K perp to the power 5 and 1 K parallel here, and this 2 energy squared and divide by omega, okay. So, now from this I can derive the formula for energy spectrum, which is given here is K perp to the power minus phi half and a K parallel to the power minus half, this guy. So, that is the prediction. This is by Galtier 2003, and we did simulation and we find a similar spectrum in our simulations, okay. So, this for very high rotation, we will not get this for low rotation, because high rotation has the Coriolis force will be too dominant compared to fluctuation, and that is where we will get this formula, okay. So, this is a simple illustration. In fact, the derivation is not too long. If you just follow this procedure, we can get this derivation, I mean we can derive the spectrum. Of course, you have to be careful with this K perp K parallel for this quasi 2D, okay. Now, let us do another one, which is called inertial gravity waves. Now, in earth actually, in fact, in earth there is a gravitation field G acting this way. So, it turns out dense fluid is below and lighter fluid is above, okay. So, if there is no motion, then it is going to be just a stacked up flow, right, density decreasing with height. Now, you put some perturbation, like the wind is blowing and that will give some perturbation, and this creates something called internal gravity waves. Internal gravity waves is very similar to water waves in ocean, but ocean water surface is there is air and water, right. There is a two different fluids and the interface is water waves, but in atmosphere we do not have an interface, right, it is all air. So, there these waves are within the bulk, okay. So, this basically the fluid is going up and down. This is along wave number is along that direction k, but of course, wave number can also be along some arbitrary direction k, okay. This is allowed, and then we will have to take the components, okay. So, internal gravity wave is basically like water waves, but within the bulk. In ocean also we find these waves within the ocean. Now, it turns out we can derive all this. So, the dispersion relation for internal gravity waves omega is n sin zeta. Now, the zeta is the same angle zeta, and this is k and this is omega, this is no sorry gravity direction z, okay. So, what is sin zeta? Sin zeta will be k perp by k. So, for rotation we had k parallel by k, and here I got k perp by k, and the derivation is very similar. We can just repeat that calculation. I am just writing the same calculation. So, here I replace by k perp by k, okay, and you can do the algebra and you find this this formula, okay. Now, we can invert it and you can get the spectrum like this, k perp to the minus 2 k parallel minus 1, okay. Okay, so this is the prediction from weak turbulence theory, okay. So, this I have not dug in to look for some numerical verification, somebody would have done it. I do not have a reference right now. Now, slightly more complicated thing is surface gravity waves. Like in the ocean we have on the surface we have surface waves, right, ocean gravity waves. Now, this is definitely quite complicated. The reason is we have, so by the way, just to give you a gist of the thing. So, we have two fluid, one is air and water, and we have two different pressure above and below. So, to derive this surface gravity wave is pretty complicated, but So, it has been derived, of course, it is a textbook material. We can find in a standard fluid mechanics book, you will find the derivation, which is reasonably complicated, but I am not going to get into the derivation of surface gravity waves, but with all that algebra it turns out. So, this is a paper which I am trying to refer to, Zakharov. I told in the last class that he is the person who started this whole field of wave turbulence. So, Zakharov gave this equation where the nonlinearity in real space is phi to the power phi cube, phi cube. So, the Hamiltonian is phi 4. So, in fact, it is phi 4 theory, time dependent phi 4 theory. So, our interaction is phi cube. So, d by dt plus I. So, we have some motion. So, I need to write d by dx of phi times the velocity of the wave, okay, and right hand side is phi cube. Okay. But it turns out the frequency, the omega k is not linear in k for surface gravity waves. The omega k is square root g k. Okay. This is a property of, this is a dispersion relation, it is square root k, and the nonlinearity phi cube is going to be convolution with 3 phi's, phi k1, phi k2, phi k3. Okay. Now, so far for hydrodynamics we have u dot grad u. So, in Feynman diagrams we write this u and u, bit easier to handle, but now I have 3 of them. Okay. So, we can, but it is possible to do this algebra, it is pretty complicated algebra, but I try to simplify it. So, now here this is something which you should keep in mind in wave turbulence, that we have something called particle density. Okay. In quantum mechanics we have wave function psi. So, psi mod psi square is a density of the particles, right, you understand. So, it is like a density of the wave function. So, it is proportional to particle density. Yes. Is k, of course, that has to be the case. K1 plus K2 plus K3 is equal to k, always convolution has this property. Okay. So, remember this is a density, and what is energy? Okay. If the frequency is omega for this for the mode, then h bar omega mod psi square, right. For photons, each photon has energy h bar omega and density of the photons, particle density. So, this is n k. Okay. So, this is what I write as particle density n k, and this is proportional to mod phi square. Okay. But what is the energy? So, energy I need to multiply by this, well, in quantum mechanics I write h bar omega, but here I write just omega. So, we can dimensionally we can get that energy stuff, but you just write omega without getting into complications. So, omega k, but origin is that quantum mechanics formula, okay, omega k times particle density. Now, we have for linear problem we have two conservation laws, n k as well as energy, both are conserved for linear problem. You put nonlinearity, then of course there are variations, but we have this both these conserved quantities. So, now I need to have two spectrum, one for particle density, one for energy. Okay. So, now let us look at, so it is easier to derive formula for n k, evolution for n k. So, so if I derive it, then I get d by dt of n k, which is d by dt of phi k multiplied by phi star k and add complex conjugate. So, what is going to happen in this process? The linear part will go away, but the non-linear part will remain, and the non-linear part will give you 3 phi's, which was just before. I am multiplying by the phi star k and real part of this, right. I mean, this is we have done this many times in this course. So, this is the energy transfer, well actually is not energy transfer, is a particle density transfer to k. So, particle density can change because of this term. So, this is basically d n k by dt, fine. But we have quartic interaction, 4 waves are interacting, right. So, we write these 4 waves like that, like this, phi k1, phi k2, phi k3, phi k4. Now, what is this value? So, we can work it out under linear approximation. So, it turns out, so if I assume Gaussian approximation, so which is assumed all the time, okay. We did this in the course for statistical field theory, well not course, in this course for statistical fields, we assume the phi to be Gaussian, and for Gaussian fields what do you assume? So, I am just basically doing the average. So, what will happen to these? Product of 4 phi's will be sum of products of 2 phi's, correct. So, I have it here, okay. So, well I can do the flux by integrating this, but the idea is, okay, I think is the next line. So, I will get this, so I get these deltas, okay. So, I got this okay. So, here, so how do I do this, okay. Now, to 0th order, so we need to keep this mind, to 0th order, so I skip that step, to 0th order I will get 2 energies, right. In fact, I have done in my other example of Schrodinger equation, but this will involve 2 correlation functions, right, product. So, phi k1, phi k2 average, phi k3, phi k4, phi k average star, okay. So, this will give you that k2 should be minus k1 and this is real number, this is real number, okay. So, so I get I was a bit lazy actually, I should have looked at this full thing, but where is this Ck coming from? So, phi k, so this is going to give us omega k coming from there, phi k. So, this is using Green's function. In fact, so the real part, okay. Okay, the idea is the following. So, to get this formula we need the following, okay. So, I need to expand it. So, I write this these four functions phi k1, phi k2, phi k3 and phi star k, okay. Now, we expand using Green's function. So, I do Green's function and this is going to give me another 3 phi's, right, and 3 phi's will come from this side and they will merge together, okay. So, these 3 correlation functions are here, Ck1, Ck2 and Ck, okay, and this delta omega is the frequency which is coming from omega, this is going to be omega k1 plus omega k2 plus omega k3 minus omega k. So, this will be minus omega k, okay. So, that is delta omega. So, these 3 correlation functions are coming from this first order perturbation, okay. So, what I was trying to get to, which is not clear to me, if I just compute to first this order, then I should get some value which is unfortunately is not what is here, okay. So, we can get this T will have 3 correlations and 1 delta omega, this following the standard procedure, okay. So, I can compute the flux, flux is the integral of Tk from 0 to k, this stuff. So, how many k primes I got? I got 1 dk prime and 3 dks, and I have got these correlation functions. Now, I did in the last class. So, dk is dk times k to the power d minus 1 for any dimensions, right, is by definition isotropic. I do k d minus 1 dk, and Ck is E k, or so whether this correlation is particle density phi square is particle density, it is not energy density. So, Nk divided by k to the power d minus 1. Okay. So, this k to the power d minus 1 cancel with this k d power minus 1. Okay. So, that is what happens. So, this 3 will be Nk cube, this one. Now, I got 1 k cube here and 1 k p cube here, right, this sitting there, and this delta omega will cancel with this omega. I need to go back. So, this is for the energy, this Tn is for particle density and this T is for the energy. So, I need to multiply omega, and this omega k is cancelling with this delta omega. Delta has 1 by omega. So, this is cancelling. Now, here I am going to get 3 k's. Okay. So, one delta function will disappear because of this condition, delta k1 plus k2 plus k3 minus k. So, one of them will go away. So, I get k cube here because of this dk1, dk2, dk3. So, I will get k cube from these guys. So, I get k cube, k cube, k cube. So, k to the power 9. Okay. So, Nk is k minus 3 epsilon 1/3. Okay. So, that is what Nk. Okay. This epsilon is the energy transfer rate or energy cascade for the energy. Okay. Now, we can do some for energy. I need to multiply by omega k, right. So, Ek is Nk multiplied by omega k. So, that will be this. So, when I multiply this, so there is a k minus 3 and square root of k, that gives you k minus phi half square root g and epsilon 1/3. Okay. So, this is the energy spectrum for water waves. Okay. And here we assume that there is a constant cascade of energy, that is an assumption, and that will work if you have enough range. If your dissipation is weak and you have enough energy to push the waves. Now, the story does not end here. This is for the energy spectrum, which is in the forward direction. It goes from large scale to small scale, like Kolmogorov 3D, energy goes from large scale to small scale, and the spectrum is k minus phi half. But it turns out in weak turbulence, if you have two conservation laws, for nonlinear term if it is turned off, then two conservation, we have one energy conservation and particle density conservation, both are conserved. Okay. So, that is a additional thing in weak turbulence. The one with higher k, so Ek is Nk times omega k, which is square root Gk. So, I am just giving you a rule of thumb. Okay. I mean, the proof you can not, it is not a proof, but the more detailed argument is given in Nazarenko's book. But you typically find that one with higher k, which allow higher dissipation at large wave numbers. So, higher k guys will go forward direction. So, Ek is forward direction, but what happens to Nk, which is conserved quantity, that will have inverse cascade, which has lower number of k. So, look, this is some k to the power minus alpha. So, it has lower weight k dependence compared to Ek. So, particle density Nk has an inverse cascade. Okay. It happens in 2D turbulence. 2D turbulence entropy goes forward, which is Ek times, entropy is Ek times k squared. Okay. What is it is squared? That is forward, but energy Ek is backward in 2D. So, similar motivation leads you to a conjecture that Nk has inverse cascade. So, that is inverse cascade of Nk, and we can derive in the following the same set of logic. So, particle flux, I am going to assume particle flux to be constant, and then similar arguments, but here I am not multiplying omega k. Okay. So, that was earlier slide was energy spectrum or energy flux. Here I have particle flux, and do the dimensional counting, and you find the zeta, it is that, I mean, okay, you can just do it carefully, you will get this stuff, and the particle number is this pretty complicated looking formula. 17 by 6 is around minus 3. 18 is 3, so that is a formula. Okay, so this pretty complicated set of arguments, but you can get the spectrum by applying this logic. So, we assume that there is a constant flux, which is an assumption which will work with uh, work under the assumption that there is enough nonlinearity, weak but enough nonlinearity, and the dissipation is at very distant scale. So, you should get dissipation should be far away. Okay. So, basically for this classical problem, so we have waves phi k, so phi k squared. Okay. So, this is the spectrum. For quantum problems, we will have particle density. For example, for photons, we have photons of different frequencies and they have different distribution. No? So, in fact, the Wien's distribution, right? I mean, what is Wien's distribution? Is like that, or black body radiation. These are particle densities. Okay. So, photons of different frequency, they have different number density. So, for water waves, of course, look, this is the part, this tells you what the part that's amplitude square is dropping as k minus 17 by 6. So, high frequency waves are less common. So, the frequency, low frequency waves are more common, that is what it means. They have more energy, that means their density is more. But indeed, I mean, this is not quantized, so you can't really say particle density. Particle density makes sense basically in quantum mechanics, it's true. Okay. Any other question? Okay, so this is the end of this topic. Okay, once you have particle density, we can get Ek, and so let's summarize this. So you can apply weak turbulence theory to many applications. I am going to do one more example, nonlinear Schrodinger equation, and then a possible inverse cascade, right. So if you have two conserved quantities, then there will be a possibly inverse cascade and end.